Hello, everyone. It's my honor to give you a presentation today. My topic today is Aztec. This is a platform to render the biomedical software findable, accessible, interoperable, and reusable. Today I'm gonna go through the overview, the Aztec features. The engine of Aztec is called Aztec IR, and also two different text mining projects on domain classification and tag generation. To give you an overview of Aztec, B2K Aztec is an amalgamation of A to Z technology, and this is a global biomedical resource discovery knowledge base. And the resource includes web services, the standalone software, and the libraries. And our purpose is to make the resources findable, accessible, interoperable, and reusable. This diagram gives a quick overview of Aztec Structure. The web application of Aztec provides an interface to search for the tools. Users can interact with Aztec through a web application or directly through an API. The initial resources were retrieved from four primary sources, like the NNH BD2K and other NNH supported programs, the scientific literature mining, author submissions, and federated global resources. All of these resources are stored in our databases and indexed to support an integrated and powerful search service. Here are some basic features of our Aztec. First is, of course, the search. We can do auto-complete for query, and users can search by keywords, by specific fields within results. And we also have ontology highlighting function. Users can submit resources by themselves, and we have the publication PDF uploader. There's a logging system. We also use Google Analytics to track the site traffic and also the top tools. We have a feedback submission system. To give you some examples of the functions, this is auto-completing queries. If you just type in the protein interact inside the system, and it will give you an auto-completing of the resources, which is most similar than the word you type in, and also the tags. You can just choose something, and the page will directly go through the resources and tags. This is a search. You can search your results based on the domains, based on the platforms, the language, and also sources. In the ontology highlighting, we mark some phrases or important words with blue. And if you want to know more about the word, the post-translational modifications, you can just click it on it, and the page will be directly linked to the BIOT portal. To give you a detailed explanation of this phrase, it has synonyms, it has definitions, and also the label something. This page is about the resource submission and editing. Users can submit their own resource and just fill out all the information here. The resource name, the description, and some tags you want to add. And we also can do the metadata extraction from PDF. And this is interface. You just submit the PDF inside, and we can do the automatic extraction to fill out some metadata for users, like the authors, like the institutes, or tool description, and so on. We use a Grobit This is a public tool which can be used here. In the Google Analytics, we track the most viewed resources and the site traffic. This two graph was shown on the first page of Aztec. Okay, here comes to our search engine, Aztec IR. And why do we want to do this? Basically, we are doing the keyword search on the description of tools. However, sometimes the descriptions of the documents can be very short, and it is quite likely that the keywords entered by the user are not inside the document. So the retrieval performance will decrease. One potential way to solve the problem is automatic document or query expansion. However, we cannot find any open access resources that perfectly meet our needs. And our previous search system, the Solar, does not perform well. So we think it is necessary to build our own information retrieval system. And here's the workflow of the system. The Aztec IR workflow can be applied to search and document similarity in domains outside the bioinformatics. To customize the Aztec search for the bioinformatic domain, we built two corpus with resources mainly from the PubMed and Wiki. This whole system has three components. The first one is a thesaurus builder. The second one is a doc-to-vec converter. And the last one is a document retriever. In the first component, we will build a thesaurus, which includes all the necessary knowledge of our specific domain, including some dictionaries of similar terms, or dictionary of hypernym, hyponym, or synonym. And then we convert the raw text into high-dimensional vectors, both for the documents and the user's query in the second part. Finally, we evaluate the similarity between the expanded query and all the documents. So I will introduce more details in the following. In our system, we utilize two corpus. For the first one, we will use it to build thesaurus. We expect it could be large enough to cover all the knowledge of bioinformatics field, especially the reasonable phrases or semantic relationship between the terms. So we extract extracts from bioinformatics, from BMC bioinformatics, nature, biotechnology, or the plus computational biology. It has much more tools than the other journals. And we also combine them with a description of tools in our Aztec system. Totally, we got more than 35,000 documents. In the corpus 2, it's all about the description of tools in Aztec, which we will do real search on. After we send the corpus 1 into the system, it will first be tokenized. Then the system will combine words into phrases. And the chi-square test is utilized in the phrase recognition step, which is a classic statistics-based phrase mining approach. We detect 4 types of co-occurrence frequencies, so 011 to 022, and calculate the chi-square value for all possible phrases as in the following formula. Then, if the support of the K plus 1 gram and the chi-square value are larger than thresholds, we consider it as a reasonable phrase. In this way, we totally got 6,068 phrases, with maximum length of 5. Then comes to the preparation of the term expansion. Firstly, for each word or phrase, the similar terms and their associated similar scores are stored into the thesaurus. Then we also build synonym, hypernym, and hyponym dictionary based on the public resources like the Wikidata and the Mesh. There is an example here. If we want to expand the query, conclude heart disease, we firstly find some synonyms, for example, the cardiac disease, and the hypernym, the cardiovascular disease, and the hyponym, the cardiomyopathy. And we collect all the words together and to make the information richer. So the search performance will definitely increase. In this stage, we want to expand the sequence with synonym, hypernym, and semantic similar terms. One thing I want to emphasize is that we do not expand the documents with hyponyms. Imagine a tool is related to the genomics. We cannot say it is also related to epigenomics, which is a hyponym of genomics. But for the query expansion, the hyponyms are utilized since users are likely to look for information from concrete categories of genomics. When coming into the stage 2, we try to convert documents into vectors for similarity calculation. We use a text rank, which published in 2004, to evaluate the importance of each term from a given document. It is graph-based keyword extraction method. It first builds a complete graph where each term is a node of the graph. The weight of each edge depends on the distance between pairs of words that occur together within a certain window. And Google PageRank algorithm is also used to assign a rank to each word. In this way, a keyword that better represents the content of the document will get a higher weight, regardless of its frequency. Lastly, the importance of each word is defined as elements into each document vector. After the expansion for the query and each document, we got an m-dimensional vector with m equals to 26,067, which is the size of our vocabulary. According to our experiment, we found the scale product performed better than the cosine in evaluate the similarity. You can see the formula here. The rank equals to Q multiplied with WI. Q is a query vector, and the WI is ith document vector. We just compute the inner product of these two vectors. Here's the result. We experimented on 12 chosen topics and evaluated the performance of our system, solar and 2 interval systems. We can say the performance was improved a lot from last version of the retrieval system. And the yellow color histogram is our results. You can see it's much better than others. We let several experts in bioinformatics to evaluate our search results to give us a rank of each query. And then we calculate the accuracy on the top 5, top 10, top 15, and top 20 results. Here comes these 4 graphs. In the whole process of Aztec IR, we mentioned a concept which is a similarity of tool. And we can also leverage the description, the tags, the tool name, the domain, resource type, and so on to provide a similar tool feature. And here's an example. For the RNA scan, we can find 5 different other tools which shares a relation, shares similarity with the RNA screen. And this similarity will also be used in the next project, which is the domain classification. The motivation of this project is to better manage our database and improve the search results for similar tools within the same category. Our original dataset has about 6,000 items, among which only 1/3 of these tools have domain descriptions. Here is a domain distribution analysis graph. It is obvious that the data is biased. You can see the genomics and the proteomics are in the majority. And this phenomenon just increases the difficulty of our classification. To show it more clearly, here's another distribution graph. You can see that there are some tools that both in the category of genomics and proteomics, which is in the orange color. Then we developed the semantic similarity recommendation system to complete the classification task. In Aztec IR, we expanded the document vectors and saved them. We leveraged this accurate feature space for representing the short text documents and also for similarity calculation. For each new tool, we took the top 5 most similar tools and used the majority of the domain size of prediction. Here is an example I want to show you about the Q-based algorithms. This package is based on the Q-based algorithms published by Hellemans etc. in 2007, and we want to predict the domain of this tool. So we index all our database and find the most similar 5 tools. The first one is MedME, and there are some raw RT-PCR data and some other tools. We can notice that the majority of the domains are recommended by the system are genomics. There are 4 of them contains this domain. So it is more probable that we would predict the domain as genomics in the end. To further improve the prediction accuracy, we need to carefully assign the contribution of each similar tool towards the final prediction. Parameters of beta 1 to beta k are assigned as a weight for the voting relevance of each of the k most similar tools with a 5, k equals to 5 here. Then we build a customized knowledge regression model to minimize the overall prediction error. To compare our classification model with some other methods, we had trial on 3 baseline models: the TF-IDF with logistic regression, the text rank with logistic regression, and label latent Dirichlet allocation. We mainly developed the logistic regression on different feature space. For example, the first one is the TF-IDF feature space. TF-IDF equals to the value of TF multiplied with log n over DF. TF here means term frequency, that each term show up, how many times each term show up in a document. And the df means how many documents contains one term. And to leverage this information, we can calculate a value for each word to represent the importance of this word in the whole corpus. And each term has a score. So for the whole document, each shouldn't have a score, and the document can be transferred into a vector, into a feature space, which can be leveraged to do the classification. The second example is a text rank with logistic regression. We just replaced all the TF-IDF values with the scores from the text rank we introduced before in the doc-to-vec converter, which is more powerful methods to calculate the importance of each term. And the third method is very popular methods currently for topic modeling, LDA. And labeled LDA is a supervised version of the latent division allocation. It constrains LDA by defining a one-to-one correspondence between the LDA's latent topics and uses tags. You can see the results here. The LDA work worse, but our SSR and the SSR with logistic regression outperforms all other different models. There's a quite high accuracy of 87.5 here. Okay, here comes to the in progress project, which is the tag generation. Aztec system used to leverage the keywords from the paper to act as tags for online resources. However, the phenomenon like tag absence or wrong tags is ubiquitous. We also want to normalize the vocabulary used by different tool description. Therefore, we are devoted in extracting the meaningful and easy retrieved tags for each of the tool in database and build a mechanism for automatically generating tags for newly submitted resources. Here is an example which about pseudonym analysis efficiency learning. And you can see there are some tags listed here. The tags like features, like the predictions, are meaningless. So we want to remove these meaningless tags and to add some more important keywords here. And this example will be continued in the following. In the training process, we firstly use the Grobit. I mentioned for the PDF submission abstraction parts, and we revised the Grobit to attain useful and clean text information from each of the paper resources. We first transform the PDF into the HTML, and not HTML, it's XML, and to the text cleaner. The module of phrase segmenter is optional to combine words into phrases for optimizing the keyword extraction. Then we use the rake to generate about 50 raw keywords or phrases for each document, and also train document and word embeddings at the same time with doc-to-vec. Now this doc-to-vec is different from the one we mentioned before. This doc-to-vec is optimized version of word-to-vec introduced at 2013. And with all words embeddings, we can easily calculate the average embedding vector for each key phrase, and then calculate the cosine similarity between key phrase embedding and the tool document embedding. In this way, items with low similarities, in another word, with little relationship, can be filtered out. Finally, 5 to 10 tags will be maintained for displaying on website. One thing I want to mention here is after the similarity filter, we can also see a lot of duplicate, not complete duplicate, just partial duplicate items inside our results. So we develop a duplicate detector to optimize the results. After users submit new resources, the system can also automatically generate the document embedding inferred by the pre-trained doc2vec model. So the process will be fast. Then it is the same procedure to return the top 5 to 10 tags to await the user's selection. This is a whole process, our tag generation. To give you more details of the tag generation, we firstly use a doc2vec embedding. As you can see in this graph, this is based on the word2vec model, and we add a paragraph ID here as work as just like a word, like an item, the same as the cat set, and we put all the matrix here and then concrete word concatenate to predict the next term of on. The mainly concept here is to use the context to predict the word to maximize the probability of the next word. After we got all the embeddings, all the vectors of items, then we will calculate the cosine similarity. On the left side, there is a list of raw key phrases or keywords that are generated by the rake, and we want to filter out the results to make it meaningful. And on the other side, we calculate the document embedding for this document 1355. And we calculate the similarities between each term and the document. We use this formula, the cosine similarity, to calculate the similarity. Here's some preliminary results are shown here. There's a comparison of the current and the old tags. You can see from the first one, the features, the predictions are not here anymore. And we add some uneven distribution, shared ancestry, which is more meaningful than the past ones. To give you some more results, this one is about the slide sort. All pairs similarity search for the short reads. In the previous results, the short read even didn't show up, but here it showed up. There's another example about the differential gene expression using the Gaussian processes. And the stationary Gaussian kernel is very important in this paper, in this tool, so we list it here. And the times are kind of duplicate and meaningless. So this is all for my today's presentation. And if you have any questions, please just ask me. Thank you.
Thanks, Joey. Do we have any questions?
Hello.
Hello?
So when do you think this will go into production?
Now it's in a beta test. I'm not quite sure about the specific date, but it's gonna be soon.
Okay.
Okay.
Any other questions for Joey?
Okay, I've got one other one then. I was interrupted in between. I'm not sure you mentioned it. How does the new system compare in terms of indexing performance to established systems?
You mean by some other systems? Actually, we just do the comparison between our system and some basic search system like the Solar.
Yeah, I saw that you compared the accuracy,
Yeah.
and that was quite nicely documented. But what about the indexing performance, the time needed? Did you demonstrate that? I might have missed it, but
Yeah, I don't demonstrate this one. And we didn't do any test on it, but I think it's a very good direction to further evaluate our system.
okay, thank you.
Okay, thank you.